Perhaps you remember the cartoon bumpkins of the Scrumpy adverts from Bywood Electronics and British electronics magazines in the latter half of the 1970s. This was the first single-board home computer kit made in the United Kingdom using the little-known SCMP or SCAMP microprocessor released in 1976. Tragically, its designer, John Miller Kirkpatrick, died young. There are very few known to survive today. In fact, this one, owned by Mike, who built it into a cigar tin and featured on the Sun, Moon, Stars Observatory webpage, may be the only Scrumpy model one out there. A couple of us on the Vintage Radio.net forum have been creating a modern replica. From my early breadboard and Veroboard experiments, Phil's beautiful PCB sprang to life for him in France. This video is to show the assembly and operation of mine in Wales. The kit consists of 16 toggle switches of several types with 13 chips and sockets. You can see the 40-pin SCMP on the right. It has mostly 4.7k resistors, 2 ceramic decoupling capacitors and one for the on-chip clock, an electrolytic for the 5x5 slow and single-step circuit. The board is single-sided, so needs around 20 wire links. The links, resistors and sockets are added first, which is a little time-consuming, hence the time-lapse film. Finally, the capacitors are added, making sure to get the electrolytic the right way around. Well, now we've assembled the worst of the board, it's well worth just checking with a multimeter on continuity that there's no short between each of the data connections. As the last thing you want is a locked data bus, and the address bus as well. The switches need to be tacked in place to get them straight and make sure the momentary action ones are in the correct place and orientation. The LEDs usefully set with a book and tacking on each end. Splaying the legs allows them to hold in position while you solder and finally trim them off, creating a pretty well ready to go assembled board. Okay, some basic checks needed on the board now to make sure if we apply power that we've got ground +5 and -7 volts correctly on the board. We've got those on the ground pin, so now we should get with ground, we should be able to see on this pin here 5 volts on pin 20 for the IC1, and on here -7 volts spot on pin 40. We'll also have 5 volts on the top right on each of the memory and buffer chips, just to make sure it's all getting on the board okay. Yep, it is. Lovely. Okay, so next we can proceed to disconnect the power again, and we'll start looking at some of the clocking chips. Install ICs 2, 3 and 4 only, and put the 5 volt back on. IC2 is going to be the 74C00, which is this one. New, so we'll bend the pins a little bit, taking obviously on anti-static mat because we got they are CMOS chips. So IC2 going in. Okay. Just looking for my IC inserter, which I normally got handy for doing these, which are much easier. But there you go. So nice and firm press, make sure they're clicked in, yep. And then we've got the IC3, which is the 74C74. It's that one. Again, it's a newish chip, so okay. And obviously we've got the 555, which is IC4. In nicely by here. There we go. So now if we apply at least 5 volts to the board. We don't need -7, so it doesn't hurt having it on there. Okay. We should be able to see with a multimeter now pin 1 and pin 2 of IC1. Yeah, 5 volt. Also we have -7 volts still on those, which we've checked. So pin 7 on IC1 should go low. 2, 3, 4, 5, 6, 7. If we press reset, which indeed it does, so that means we're seeing a drop to 0 volts every time we press the reset button, which means that the 74 C00 is also working, because the gates, 2 of those gates are used to debounce the reset circuit. So it's excellent. So if we put the slow switch in the down position, so pin 3 on IC4 is indeed oscillating between 5 volts, so we've got a nice oscillation there going. So, and we should be able to see 5 volts on D7, which is, we're going to have to look at the pin out, but D7 is actually on pin 9 of the IC, so 1, 2, 3, 4, 5, 6, 7, 8, 9. We need the run halt up to do that. Yeah, so when it's in the down position, we got 5 volts, so that's fine. There we go then. Right, well that looks like that board is pretty much running. So we can put the remaining chips in, all except them 2 memory chips, and you don't actually need the I/O latch chips at this point either. They're used for interfacing work. I did in the end find my IC insertion tool to make it quicker and simpler. Okay, now we've got the board assembled and the chips put in. We can power up the board, so we put the ground in, and -7 and +5 obviously, because we've got to power all the chip up. So off we go, ground, 5 volts, -7 volts, oops, there we go, lovely. So the machine's reset. Now it's on address 1, but we push the reset button down, and indeed it does. I should have had all the switches up, which I have now, the data switches, so when we do the reset, we do see it go back to address 1. I should be able to hit the step button, and it'll move forward to the next address. It's executing instruction 255, obviously, as all the bits are set, and that means it jumps around in RAM a little bit. But if we hit the reset button again and put all the switches down, then effectively we have a halt instruction that's being sent to the CPU. So if I step it once, it'll move forward. Yep, it does indeed. Running the halt instruction. Now if I set the run halt to upwards and step, it'll continuously run, and you can see A11 flickering because it's accessing every address, running a halt instruction. It's doing it just fast enough that only the last few address lines, A10, you can just about see flickering, possibly, depending on the camera. So if I put it to run halt to the centre again, it'll stop at a random address in memory. And if we press the reset button, we'll go back to the start. So we're looking good. Looks like it's operating. There's a few tests in the manual you can do to put particular instructions on the bus as well, just to try a few little things. But I think we're about ready to get the memory inserted and actually try writing some data into memory and let the CPU have some programs to run. Okay, I've just installed the RAM chips. You may have noticed last time I did it the wrong way round. I still had the power supply powered up when I plugged it in, so it's already plugged in. And now I will turn it on, which should improve things a little bit. There we go. So we're back now. We've got some random data in the memory by the looks of it. So we actually had a value on the LEDs, although they're disappearing a bit. Okay, is that because it's fading? I don't know. Okay, ooh, things are coming on and off. We've got a little bit of random data there. That may not be a very good symptom. Okay, loose connection perhaps somewhere. Could be. Okay, let's try writing a 0 into memory and put it back up again. Nope, doesn't look good. Looks like we may have a faulty RAM chip. Okay, let's unplug them. Okay, well, it's a little bit closer to the board now, and we've got 2 replacement chips for our these ceramic 2112s are faulty. We've got a pair of standard AM equivalents, I think they're 9112s. They're known good from one of the other machines, so it seems to be correct now. When you reset, go back, there's nothing shown in RAM. If they're all ones, the data switches, we do a load, or the RAM first address changes all to ones. If we step into it, we got a random amount of data in the second data, just as random data in the RAM. But if we scroll the switches down, set the machine to run, and then just do a step so it runs completely, and hit load, we should load 0 into every address now, so it's flickering. Okay, so when we halt it halts at a random position in memory, do a reset, all the data switches up, and memory should now step through slowly, containing just the address lines going up with no data in it because the memory has taken a 0. If we reset and try and just put a particular value in, so we just put maybe 0, 0. So we're going to put 1, 2, 4, 8, 16. So if we put 8 in, which is a NOP instruction, and press load, indeed we end up with that particular value in. So we go back and we push all the switches back from ones, and indeed we've got that. And the next step through to the next instruction, we still got 0. So the RAM is now running fully. We'll have to investigate whether it's one or both of those RAM chips that are faulty. It's a shame. Okay, well, by a process of elimination, one of the RAM chips was definitely faulty. Luckily enough, we got a little stock of the old ceramics, so now the board is complete and has got all of the parts and is running fine with the original chips. So the only thing we haven't put in is the buffer chips because we're not actually using them, but we'll probably stick them in now just to make sure that they're ready and they don't short the board out. They might as well live on the board. And obviously the PSU is humming away there quite nicely to provide machine. When I hit reset, it goes back. We can set any value we like on the data switches and press the load button, and then when we go back to that, it'll retain it in the RAM now. So it's fairly easy because obviously it was this one chip. I had swapped them both out just to prove it wasn't actually a board fault, and then I put them one at a time, and you can easily see it is just one bank of LEDs because it's the lower 4 bits or the upper 4 bits depending on which chip. So this one's the upper 4 bits, IC6, and IC5 is the lower 4 bits. The Scrumpy one in this advert was developed further to use the SCMP2 chip and EEPROM based programs. Eventually, it culminated in the Scrumpy 3 with an ASCII keyboard and display on a domestic television over a year before Sinclair launched the ZX80. So if you want to build one, to know more or contribute to the preservation effort, then it's well worth reading the Register article on Miller Kirkpatrick. Visit the preservation website at scrumpy.uk and visit us perhaps on the vintageradio.net computer forum.